Okay, so let's continue on the last topic, Fourier transform. Okay, so we'll finish that shortly, and then I'll do a quick review. Okay. So the definition of Fourier transform is this: if you have an aperiodic function f of t, then you can take the so-called Fourier transform using these integrals at here. You're transforming basically from a t domain, a t function, into a omega function. Okay. So the idea essentially is you're looking at a different information, okay, for the same function. And f of omega is a complex number. So a complex function of omega. Okay, so at the different omega value, you will have a different f omega as a complex number. Okay. And I showed you actually also how this formula is derived. Okay. So the Fourier transform can be obtained or transitioned into from Fourier series. Okay. So you could basically, the idea is you could actually from Fourier series, okay, to Fourier transform. Okay, there's an analogy here. So updated my lecture notes. So for example here, let's say we have an aperiodic function. If this is a function f of t, that's aperiodic, right? And now we make it a periodic function. So we basically create mirrors of this f of t and make it a periodic function with a period of t. Okay. So then we can take a Fourier series of this periodic function. Okay. This is basically the complex form of Fourier series. And we can get the values of the coefficient d, d naught, and dn like that. And then giving a specific value, for example, if a small d is 1, and capital T, we'll keep it as a variable. Okay? So as capital T changes, as you can see, basically the period, if the period start to increase, so this box, the distance between the two boxes will start to be larger and larger, right? So as t goes to infinite, then this box is like it goes to infinite, disappeared. Then you're only left with this one. Okay, so that's why we say f of t, right, equal to the limit t go to infinite and f of t here. Okay, so that's the transition basically from Fourier series to Fourier transform as t goes to infinite. So what happens when t goes to infinite then, right? So I did a little bit graphing at here to illustrate the effect of the period t. Okay, so here's a few graphs here. For example, if t equal to 2 seconds, right, this is basically very spatially arranged, the periodic function based on the original box. Okay, so this is t equal to 2 seconds. Then we can graph the magnitude of the coefficient of that complex dn, complex coefficient dn. Okay, so this is what it looks like. But when t is 5 seconds, right, start to space out, and this is the magnitude amplitude spectrum. Okay, so you see that it's looks much smoother now, right? Now keep increasing t. If we keep increasing t from 8 to 32 seconds, so at the 32 seconds, the range of the graph, you don't see that f of the periodic function anymore. You only see this f of t here. but at t equal to 30 is 2. You see, this is basically, it's still discrete, right? At each omega, you still the discrete drawing, but altogether, this is like a continuous drawing now, right? Continuous spectrum. So if t is much larger, then you should expect it's like you have a continuous plot at here. And that continuous plot is basically a plot of this f of omega, the magnitude f there. Okay. So that's the connection between Fourier series and a Fourier transform. Okay. We also looked at a Fourier transform of some typical functions. Okay. So we looked at the Fourier transform of a delta impulse function in the last lecture. So I just want to show you a couple here. Want to show you the difference between Fourier transform, basically look at it, and then also similarities with the Laplace transform. Okay, so let's take a look at this one here. If f of t is e to the power j omega naught t. Okay, this is a very unusual function. This is not a real function. It's a complex function. Okay. So f of t by itself is a complex number if you substitute the t with different values. So let's take a look at what the Fourier transform of this function is. Now before we take a look at the Fourier transform, now this one here, right? Basically is cosine omega naught t plus j sine omega naught t. So it's a complex, but the time function, if you look at each one of them here, it has only one frequency component, which is omega naught. So that's the only frequency component in this function at here. Then its Fourier transform, okay, f of omega, then we should expect, because Fourier transform basically give you the spectrum frequency, the frequency spectrum. So we should expect this one has only one frequency, which is omega naught. So let's take a look at how we do this. We use our formula for Fourier transform, which is this formula here. Substitute f of t with e j omega naught t, and then this is e negative j omega naught. E negative j omega t and dt. Okay. And this gives us negative infinite, positive infinite e negative j omega minus omega naught t. Okay. Yeah. So from here, I want to use results that we actually done from previous lecture. Okay. So in previous lecture, we did a Fourier transform for delta t. Okay. So we did a delta t's Fourier transform. And we find in that case delta t Fourier transform basically is 1 over 2 pi negative infinite positive infinite negative j omega t dt what is it, d omega? Sorry, this is a delta t's inverse, not the inverse, the inverse Fourier transform. Okay, the inverse Fourier transform. Okay. Okay. So maybe let me jog your mind at here. Okay? So sorry, let me restart this. Okay, so given say impulse function delta t minus t naught, okay, we have, this is from previous lecture here, okay. So what do we have? We have from previous lecture we get basically f of omega equal to the Fourier transform of delta this. So you plug in this function into it, into the formula, okay, and you get e to the negative j omega t naught, okay, e omega t naught and here. So then at the t naught equal to 0, okay, so we get our Fourier transform for the impulse function is 1, right? That's what we did from previous lecture. Okay, yeah. Now when this is 1 at here, right? This is basically the Fourier transform of delta t, okay? Or you can call this is the f of omega, right? For the Fourier transform of delta t. Then you can apply the inverse Fourier transform formula. So inverse Fourier transform for f of omega, right? Inverse Fourier transform of f of omega should give you back delta t. And the formula for inverse Fourier transform is this. So 1 over 2 pi, okay, and then negative infinite to positive infinite, okay, and then f of omega times e to the power of j omega t d omega. Okay, this is the inverse Fourier transform formula. So I'm going to replace f of omega with 1 because this is 1 for delta t, right? So that's why the inverse, okay, the inverse Fourier transform for delta t, okay, is this formula here. Okay. Okay, so that's basically this one here. Now I'm going to make a little bit change of variables on both sides of this. So for this equation right here, I'm going to make a little bit change of variable. So for this equation, I will make a change so between t and omega. So mathematically it's feasible. So when you have a function like this, okay, so if I change all of the t to omega and all of the omega to t, okay, so then we can do that. Okay, basically we get delta omega, okay, equal to 1 over 2 pi and then ej omega t and dt. Okay. So it's like you're swapping the position of t and omega. So then you get this one here. Okay, you get this. Okay. So for this one, if I compare with what I'm doing at here, this is what we're trying to obtain, right? So this is what we're trying to obtain at here. So what we're trying to obtain at here, this is omega minus omega naught, and here is the omega at here. Okay, yeah. So I can make use of, basically we're looking for Fourier transform of this function, and we're trying to calculate. Okay, so let me rewrite it here. So we're trying to calculate this one. Now I want to make use the results at here. Okay, make use these results and apply to this expression. So what do? So you see here, this is omega, this is omega. The only difference is this is negative omega minus omega naught. See the difference here, right? Yeah. So basically, if I replace this omega, okay, the 2 omega at here, this 2 omega with the negative omega minus omega naught, then I get this term, right? So essentially, for the term indicated by the star, I can replace the omega with negative omega minus omega naught. And of course, there's also 2 pi here, right? There's 2 pi, so you multiply 2 pi to this side. Okay. So that's it. That's basically the results of this. A little bit of simplification. Delta function is always an even function. Okay. So the Fourier transform of the complex function, time function, give you these results at here. So what is this results? If I plot this one, right? If I plot this versus omega, this is if I plot delta omega minus omega naught. So what does it look like? It's an impulse function and only exists at omega equal to omega naught. So, and of course there's a magnitude of 2 pi here. So now basically the Fourier transform of this time function, which has only one frequency component omega naught, showed up explicitly in the Fourier transform plot, right? If you plot this magnitude and plot this function, you get just one single frequency, which makes perfect sense, right? Your original time function has only one single frequency. Okay, so that's what actually the Fourier transform is useful about. It reveals the frequency information behind a time function. When you're given a time function, right, a similar time function, you may not be able to get, by looking at it, you may not be able to see, so what is the frequency behind this time function? You don't know, right? But if you do a Fourier transform of that, and you'll see clearly the frequency behind that time function. Like the impulse function that I mentioned in the previous lecture. So for example, right, when you have an impulse signal, its Fourier transform is 1. So you see in this case, if you plot this versus omega, then you get 1 all the way across every different omega. Okay, so omega doesn't matter negative, positive, doesn't zero, doesn't matter 0, doesn't matter 1,000. It's always 1 in this case for the impulse signal. So that's why impulse signal is rich, it's literally rich, right? There's infinite frequency information behind this impulse signal, right? Not like this one, right? Not this one, just a sine, cosine with 1 frequency. Okay. Okay, so I'll show you one more head here, and then I think we can stop. I know you're all getting tired of all of these writings here. So let's take a look at this signal, exponential function. Okay. So what would be the Fourier transform of this exponential function? Suppose a is greater than 0. And I will use the formula to illustrate the Fourier transform of this function. Because this is a causal function, so there is a u of t at here, then when you plug in this function into the definition of a Fourier transform, okay, Fourier transform originally is from negative infinite to positive infinite. And because the u of t, then it becomes 0 to infinite. Okay. And that gives you 0 to infinite e to the power negative a plus j omega t dt. Okay, so you can do this integral as it is. So basically negative a plus j omega e to the power negative a plus j omega t and 0 to infinite. Plug in the limits and you will get 1 over a plus j omega. Okay, so the Fourier transform of the exponential function is this expression. So 1 over a plus j omega. Okay. So from here you could sketch the magnitude, you could look for the angle, right, at different versus a different omega. Okay, that's the idea of Fourier. So once you get this, you can plot its amplitude spectrum and its phase spectrum, and you can take a look at what type of frequency is hiding behind this exponential function. Right. But the point at here, what I make is, so you see this is 1 over this. For this exponential function, if you recall that, what is the Laplace of this function? The Laplace of this transform is what? 1 over s plus a. So a very common connection, okay, but this is not a this connection is not true for every situations. Okay, so if you look at these two connections here, if I let s equal to j omega, then the Laplace becomes what? The same as the Fourier transform. Okay? Yeah. So this is the same as a Fourier transform. So in many yes.
When is it not the same? Like forget Laplace is close to the
Right. When it's different, that's actually a really big topic. So don't want to go through the details there. The simple rule is when the region of convergence for this, let's say if we call this as f of s at here, okay? Yeah. The simple rule is a concept called the region of convergence for this function includes the j omega axis, which is the imaginary axis. Then the Laplace and the Fourier, you can replace the s with just the j omega. Okay, but that's a different story. But anyway, so it's really out of the scope of this class. But in your mind, you should bear in mind is that there is a similarity between Fourier and the Laplace. Under certain conditions, you can do this replacement. Okay, and they can be the same. But not always true. I'll give you an example here, right? For example, if I have a function, unit step function, okay, if I have a unit step function, okay, and if you take the Laplace of a unit step function, what do you get? 1 over s, right? Yeah. But if you take the Fourier transform of the unit step function, you get 1 over j omega. This is the same, right? When you replace this, and then one will term like this. So that's the difference between these two, right? Yeah. They're only going to be the same as I stated when the region of convergence for the s function contains the j omega axis. So, okay. Anyway, in application, I think I mentioned this. Laplace used very widely in control applications, but Fourier's transform is used widely in signal processing and image processing, electrical applications. Okay. So I think I'll stop here. As a matter of fact, I will not test you guys Fourier transform in the final exam. Okay, so you should relax that. But Fourier series will be tested. Okay. Okay, so I make use of the rest of the time to do a a final review at here. Right. So I don't have that much time. I will write not as detailed as my lecture notes, but I do have a separate lecture notes summarizing what we learned after the midterm. So this is just a quick recap of what we learned in the after the midterm. So we continued on the first order differential equation in lecture 16 and 17, and we covered two more types of first order differential equation. One type is called homogeneous type equation. Okay, so homogeneous. Okay, basically this function f of x, if this function can be written as this, then we call this is a homogeneous to the order of 1, or just call it homogeneous equation. Okay. And we have a ways to solve this, right? So take a look at the lecture notes. We also covered another one called the Bernoulli equation. The equation basically takes the form like this. Okay, so this is a Bernoulli equation. It's a nonlinear equation. But however, you can use a substitution. Basically, let u equal to y to the power of 1 minus n, and we can turn this equation into a linear first order differential equation, and then we can solve it. Solve for u, and then substitute back for the y. So those are the two type of equations that we covered after the midterm. There's another one called exact differential, but that's actually, we quickly skip that one. Okay. So before we start on the second order differential equation, we covered the concept on complex numbers, and this is lecture 18 and 19. So for complex number, what I need you to be able to do is, right, how do you add, subtract, and multiply, divide. Okay, so basically the basic operations of a complex numbers. And when you have a complex number, you should know that you can write this complex number in many different ways. It can be written as strict as this complex number, or you can write it using the Euler's formula. Okay, and Euler's formula basically says this. Right, this r e to the power j theta, and r is the magnitude, or we call that okay. So this is a theta here. Theta is between negative pi to pi. Okay. So this format of a complex number, okay, often in time can be used to simplify computations. Okay. I think in one of the quiz, okay, to calculate what's the quiz question? Forgot. Anyway, so a complex number to the power of a complex number, right? How do you simplify that kind of situation? Okay. More important is remember this Euler's formula. Okay. Euler's formula, e to the power of j omega t equal to cosine omega t plus j sine omega t. Okay. And we also talked about the phasor concept. So when you have two cosine term, Okay, let's say or two or one sine, one cosine. This doesn't matter. But the same frequency. Okay, different magnitude. Okay, so here they have the same frequency, different magnitude, different phase angle. How do you add them up? Okay, how do you add them up? That's using Phasors concept. You should take a look at it. Okay. This can be sine too. Okay, so this can be a sine. So there can be transition between sine and cosine. And the last concept of the complex number is, what is the nth root of a complex number? Okay. So there's a formula associated with the nth root. I believe I've included that in the formula sheet. And by the way, I updated the formula sheet, included a couple of new Fourier series formula. Fourier transform formula is also in the formula sheet, but I don't think we're going to test that. Okay. So, okay, take a look at this formula. Okay, what's the formula for this? All right, so that is a complex number, right? Lecture 18, 19, and then followed with a big chunk of second-order differential equations. This covers pretty much from lecture 20 to 25. Okay. For a second-order differential equation, in order to solve this, okay, I need you to understand the concept of a linear independent and the linear dependence. So Li and Ld. So there are a couple of theorems as basically the guidance to find the solution of a general solution of a second-order ODE. But we basically talked about two different types of ODE. One is, what is the solution to homogeneous? Okay, second-order ODE. Homogeneous, basically the right side, there's no input to the system, right? So zero, and you only have the differential equation on the left side. Okay, so y double prime plus ay prime plus b equal to 0. Okay. I believe in the formula in the lecture I use this. So, but sometimes we also have this y here. Okay, we also have a format like that, which is the same thing basically. When you divide a, then you get exactly the same format. Right? Okay, so this is a homogeneous one. Okay. So under this category, how to get the solution, right? First step is a characteristic equation. Okay, and then you look at the solution of the characteristic equation, and there are three different type of roots. One is two real distinct roots, repeated real roots, and then a pair of complex conjugate roots, right? So for each different type of roots, then you have a format for the general solution. Okay, so solution according to the types of roots. Okay, so take a look at that. Under the same category, we also look at okay, it's nothing new, but it's just we give the meaning of this, give a meaning to this ordinary differential equation, homogeneous one. We call it free vibration. Basically, when you have no input to the system, right, then the system will vibrate at its initial condition. So that's what we call this free vibration. Okay. And we use the mass spring damper system MKB, right, to illustrate the idea of free vibration. And we also have the omega natural frequency, zeta damping coefficient, right? So what's the connection between the parameters of this MBK and the omega n and zeta? Okay. So just the different ways of describing the system, right? It's still the same system, basically. Okay, that is homogeneous one, right? Homogeneous, and then we have also looked at solution to non-homogeneous. The second order ODE. Okay, non-homogeneous. So this part's pretty much lecture 23 and 24, I believe. Okay. So in this part, you need to find a particular solution and a general solution YH. So YH is basically the general solution for the homogeneous one. And YP, the particular solution, is where that you have to you could use a different approach to find YP. You can use the so-called method of undetermined coefficient. Okay. So you could use this, or you could use the variation of parameters. Okay. So there are two categories you can use two different approaches to use to find a YP. The first one, method of undetermined coefficient, there should be a table you have to use it. Okay, heavily. They would call it lucky guess approach. So you have to make an initial guess, right, based on this table. Okay, the table is included in the formula sheet, and you probably had to make modifications to your initial guess, okay, and then find the solution YP. Variation parameters, okay, is a little more general, but you do have the two formulas to use, okay, to calculate Wronskian, to use the formula, and then do the integral to get the YP. Okay, so take a look at the formula for each one of these. If you don't remember now, they are in the formula sheet, but I highly recommend that you still write a few more times. Make sure that you actually fully understand those formulas. The next large topic is Laplace transform, transfer function, and impulse response. And this is a lecture 26 to 30. Okay. So under this big category, you need to understand by itself what is Laplace transform, right? What's the definition? And what is Laplace transform of a typical functions, right? So you have the table. The table has properties and typical function. So that's Laplace transform purely by itself. But we use Laplace transform to do what? To solve second order, okay, ODE. So we use Laplace transform to solve second order ODE. And when we solve the ODE using Laplace, so there's a technique we used called the partial fraction expansion. Okay. So basically you transform your time domain ODE into the S domain using Laplace. And then you use partial fraction expansion to simplify it to the simplest form so that you can look up from the table that you're given. Once you get it from the table, you get the inverse Laplace, which is a solution. Okay? Yeah. So how do you do this partial fraction expansion under different scenarios? There are 3 different cases I believe I covered, 3 or 4, I can't remember. Right? So those are basically given a system. How do you do the partial fraction expansion? How do you find that unknown constant terms? Okay, based on the types of the system. Okay, so that's the part you need to be comfortable with. And the other part is, so how do you get the transfer function, right? What's the transfer function? From a transfer function, if you take the inverse and you get the impulse response. Okay. So simple question, given a system, write down the transfer function. What's the condition? When you write transfer function, you will assume the system initial conditions to be 0, right? And then the inverse of the transfer function is impulse response. Okay, so that's the part. We also used Laplace transform to solve a special type of ODE. If you recall, I gave you an example. When you have a stepped signal, piecewise signal, right? When you have piecewise, it's very difficult to solve if you solve it in time domain, but it's relatively easier to solve in the S domain. Okay. And then we have what we just learned in the last weeks, which is the Fourier series and Fourier transform. Right. So focus on Fourier series. There are 3 different types, different formats of a Fourier series you can write. One is the so-called trigonometric type, compact form, and complex form. Okay. So what are the 3 different forms? How do you get the coefficients for each one of the forms? Okay. Okay, so that's about it. The final exam is not going to be comprehensive, so we will not retest many of the topics we learned before the midterm. But I think we will still have a question on convolution. Okay, so using graphical approach to solve convolution. It's not going to be as a big question as, so let's for example, midterm you have 30 points for the question. Maybe for the final only 10 points for the question. Okay, yeah. But you do have all of these important topics that we learned after the midterm, right? So everything after midterm is part of the, except this, okay, is part of the final exam. A formula sheet, I will print out some, bring it to the final exam, but it's double-sided, so you don't have to print yourself, okay? And I will be around during exam time. I shouldn't go away. So if you have questions, feel free to ask. I believe everything's uploaded, all the tutorial. There's some additional exercise, assignments, lecture notes, tutorial notes. There's enough material for you to study, to review. Okay. The other thing, what's the other thing? Anyway, I can't remember. I'll send you an email. Here's another thing. So anyway, make sure you stay on top of each other, on top of your courses, but also make sure you're healthy, right? You know, this exam is very stressful period of time, and our exam is the last day of the exam period, December 17. Okay, so make sure that you're pulling up until the last moment. Okay, successfully finish everything. Okay, yeah. Anyway, so that's it, and hopefully good luck to your exams. Okay.
Thank you.
Okay.